In the first section, we introduced the basic definition of MapReduce and YANG. In the second part, I will give a brief introduction to functions and architectures of MapReduce and YANG.
MapReduce is inspired by the built-in functions map and reduce in functional languages. Briefly, in a functional language, map indicates that each element in a list is calculated, and reduce indicates that each element in a list is calculated in iteration mode. The specific calculation is implemented through the input functions. The map and the reduce functions provide the calculation framework. However, such explanation is abstract in practical usage of MapReduce. If reduce can perform iterative calculation, the elements in the list are related. For example, if you want to sum all elements in the list, the elements in the list must be numbers at least. However, map processes each element in the list separately, which indicates that the data in the list are disordered. In this case, the map and the reduce functions have some connection with each other. Okay, let's have a look at MapReduce workflow. Suppose the input is a file. We can find it be split into small tasks. And these small tasks will be operated in parallel. Each small task is composed by a map task and a reduce task. And we call the operations between map tasks and reduce tasks the shuffle. And after the two steps, we will get the final output. Different map tasks cannot communicate with each other. In addition, no information is exchanged between different reduce tasks. And users cannot explicitly send messages from one machine to another. Furthermore, all data exchanging is implemented by the MapReduce framework. Let's see more details in each step. First is a map phrase. Before job is submitted, the file to be processed will be read from HDFS and then be split. By default, the MapReduce framework regards a block as a split. Before data written to the local disk, the following operations need to be performed. The partition. By default, the hash algorithm is used for partitioning. The MapReduce framework determines the number of partitions based on the reduce tasks. The records with the same key value are sent to the same reduce task for processing. After partition, we tend to sort and combine. The outputs of map are sorted and the combination is optional in the MapReduce framework by default. For example, you can combine hi 1, hello 1, and hello 1 into hi 2, hello 2. It will be explained in the example later. After a map task is processed, many spill files are generated. These spill files must be combined into spill files, map out file, MOF, that has been partitioned and sorted. To reduce the amount of data written to disks, MapReduce allows MOFs to be written after being compressed. This is the brief introduction to map step. We can find the combine is an optional step. Actually, it can be regarded as a kind of reduce process. The other step is the reduce step. When we finish the map phrase and get some MOF, which stored in disk, then obviously we have to read them from disk first. Generally, when the MOF output progress of a map task reaches 3%, reduce task will start to obtain MOF files from each map task. The number of reduce tasks and MOF partitions can be determined by users. For this reason, the MOF files output by map tasks map to reduce tasks. Reduce step is also determined by user-defined reduce function. From this figure, you may doubt that there are a few steps before reduce like copy, and merge. What does that mean? Actually, we call some steps between the process of map and reduce shuffle. The shuffle process includes obtaining MOF files from the map tasks of reduce tasks, sorting and merging MOF files. We know that a cache is allocated to each map task. MapReduce has 100 MB cache by default. That's a speed ratio to 0.8. Sorting is the default operation. After sorting, you can combine the target data. Before all map tasks completed, the system merges the files into a larger file and saves the file to a local disk. During file merging, if the number of split files is greater than the preset value, 3 by default, the combiner can be started again. Besides, Job Tracker will monitor the execution of map tasks and notify reduce tasks to obtain data. The reduce task queries Job Tracker for completion of the map tasks through Remote Procedure Call, RPC. If the map task is completed, the reduce task will obtain data. The data merged from different map machines is sorted in cache and written into disks. Multiple spills files are merged into one or more larger files, and the key value pairs in the files are sorted. Maybe you are confused to the process of MapReduce. Let's have a look at this example. The word count app. This figure illustrates the main steps. We will explain each step in details later, so don't worry. Actually, the word count is used to analyze the frequency of each word repeated in text file. MapReduce can help users quickly perform statistical analysis. The figure shows the main steps. Firstly, we can find that file A is stored on HDFS and divided into blocks A.1, A.2, and A.3, located at data node number 1, number 2, and number 3. Secondly, the word count analysis and the processing program provides user-defined map and reduce functions. Word count submits analysis application to the master node in YUM Resource Manager, which we will introduce later. Then, Resource Manager creates job based on the request and creates 3 map tasks, as well as 3 reduce tasks running in a container. Then, map task 1, 2, and 3 output a MOF file that has been partitioned and sorted but not merged. See the table shown in the slide for details. We can find that when each word is encountered, we only need to count it once. There are 3 A, 2 R, 2 high, and 3 hello, which haven't been combined yet. When we get the MOF, we will do the reduce task. The reduce tasks obtain the MOF file from map tasks. After combination, sorting, and user-defined reduce logic processing, the statistical information shown in the table will be output. And this is a brief introduction to the word count.